everyone, and welcome to another session of this course. In the last session, we talked mostly about a very specific smart contract. We talked about lottery. In this session, we're going to talk about another very specific smart contract, and this is something that we have already seen when we are talking about contracts on Bitcoin, but now we're going to see the Ethereum variant. So the contract that I'm going to talk about today is basically an escrow contract. So let me create a new stability file. Okay. So before I go here, I just want to say one thing about the current homework that has been released today. So in this homework, you are supposed to do a security audit of a smart contract, and the smart contract that I've given you the homework is deliberately written with a lot of bugs and a lot of vulnerabilities. So your job is to find as many of these as possible. And in order to do this, there is a paper that I have put on campus that I think you need to read. Is there a lot of noise again? Okay, let's see. Is it fixed now? Okay, great. So, yeah, sorry about this. I don't know what's happening with my microphone. It's sometimes like this, but most of the time it works well. So I was just saying that please read the paper that I've put on Canvas. You will need it in order to solve this homework. And this is the only required reading that we have in this course. So it's like a 20-page paper, and I want all of you to read that. So with that being said, let's go here and let's talk about the escrow problem. So this is a problem that I have already mentioned when I was talking about contracts on Bitcoin-like blockchains. And what we want to look at here is a two-party sales escrow. So we have two parties, a buyer and a seller. We call them sometimes Alice and Bob. So let's actually write this. So let's say I have a contract called escrow, and I have a buyer and the seller. And the idea is that the buyer needs to buy some physical good from the seller, and they're going to do this in a very specific manner. So the payment is going to be done on the blockchain, but the good has to be delivered in the physical world. And now the challenge here is that if the good is going to be delivered in the physical world, there is no way for our contract to actually verify that the good was delivered, right? So if the good was already something that was on the blockchain, for example, if it were an NFT, then our contract could just verify that the good is sent, and then that would be the end of the story. But what's really challenging here is that the good is not on the blockchain. So the contract has no way of knowing if the good is actually delivered or not. And it has to rely on whatever inputs the buyer and the seller will give to the contract. So we talked about this before, and we had this idea that we can get deposits from both the buyer and the seller, and then we give the seller a predetermined amount of time so that they can deliver the item. And then after that time passes, the buyer and the seller can tell the contract whether they think the item was fulfilled or not. Okay, so let's start by implementing this, and I will try to implement it in the simplest possible format, and then we will talk about attacks and how we can improve on this. Okay, so the simplest thing is I can have let's say I have a fixed value for the item. So let's say the value of the item is 1 Ether. Okay. So what do I need? I need for both parties to put down a deposit. So I will just create two functions for the two deposits. So I would say function buyer deposit. It should be public and payable. And the buyer will call this function to make her deposit. And what we do here is that we have to basically check a bunch of things. We have to check that we have the right buyer. So let's say here that I've hard-coded the addresses of the buyer and the seller. So let's say the buyer is my first account here. And let's say the seller is my second account here. Okay. So when we call buyer deposit, we have to first make sure that it's really the buyer who's calling it. So I would require that the person who's sending this message, the caller of this function, is actually the buyer. And as we talked about this before, we want the buyer to put a deposit of twice the value of the item and the seller to put a deposit that is equal to the value of the item. So I would also require here that the value, which is the amount of money that was sent with this function call, is equal to the item value times 2. Okay, so this was for the buyer, and now I can have a similar thing for the seller. It's public and payable. And again, I just require that only the seller can call this. And I also require that the amount of money that the seller pays should be equal to the item value. Okay. And as you see, these functions are not doing anything else at the moment because all they're doing is that they're accepting the deposit and they're payable functions. So if these two conditions go through, then the money will just belong to the smart contract. So the smart contract now has it. Okay. So after we do these things, we want to give seller time until some predetermined block. Okay. So we can actually add that one as some hard-coded value here. So I can say deadline is some block number. I just write 1, 2, 3, 4. But this is a block number, and basically it's, as I talked about this before, we don't really use the timestamps because the timestamps can be manipulated by the miners. Instead, we always use block numbers as a proxy for time. So what I want to say is that the seller has until this time to send the item in the physical world to the buyer, and only after this time passes, they can actually come back and continue with this contract. So, as we talked about this before, what I want to do is to say that after the deadline has passed, each of the buyer and the seller can give the contract just one bit of data or one Boolean value that tells the contract whether they think the item was fulfilled. Okay, so I'm going to have a Boolean value, and I'm going to call it buyer's declaration, and I will have another Boolean value called seller's declaration. Okay, and I can have a function called, I just call it declare. This is public and payable. Well, not payable, sorry. This is public. So this is just used for the two parties to tell the contract if they think the item was fulfilled or not. So the first thing that we will require here is that the declarations can only be made after the deadline. So I would require that the current block number is larger than the deadline, right? Because otherwise the seller still has time to fulfill the item. And then I would just do an if. I would say if the person who's sending the message is the buyer, and let's say they are giving me also some Boolean value called declaration. If this message was sent by the buyer, if the function was called by the buyer, then I just say buyer's declaration equals this declaration. And otherwise, I say seller's declaration. Okay. But there's another thing that I have to also keep track of. And it has to do with default values. Right. So here, since I'm just using a Boolean for the two declarations, I'm not distinguishing between the case that a buyer does not declare anything and the case that she actually declares false. She declares that I didn't receive the item. And these two should be different. So I will need an additional Boolean that tells me if the declaration is made. So I would just say buyer has declared, and I will have another Boolean called seller has declared. And here I would say buyer has declared becomes true. So I'm just using it as a flag. And here I would say seller has declared is true. Okay. This is just so that I can distinguish between the cases where someone declares false and the case where they just haven't declared yet. Okay. So after these declarations are made, we talked about this before. There was this idea that if the two parties disagree, then the money will be confiscated. The contract will not pay anything to anyone. And otherwise, they can just get a refund if they both agree that the item was not delivered. And if they both agree that the item was delivered, then 2 times item value has to be paid to the seller and item value has to be paid to the buyer. Okay, so let's see how we can write this. There are several things that can happen. So first of all, we're not sure if both sides have really given their deposits, right? So before this declare, I will have another requirement. And this is just to make sure that both parties have paid their deposits. And the requirement that I will have here can be something very similar. I can just, very simple. I can say that the balance of the current contract should be 3 times item value, right? If this is the case, then I know that the buyer has paid their deposit and the seller has also paid their deposits. So if this is the case, I'm happy and do this thing. Okay. And another thing that I can do is that I can have a refund function here. So in case the other party did not give us the deposits, right? So here I can just say, so this is something that the buyer would call. I would say require that the sender is the buyer. And the idea is that if the seller has not paid their deposit, then we want to basically refund the buyer. So the other thing that I require here is that I want the balance of the current contract to be 2 times item value, which means that only the buyer has paid her deposit. And if this is the case, I would just pay the deposit back to the buyer. So I would just say buyer dot transfer twice the item value. Okay, and for this to work, of course, the buyer has to be payable and the seller has to be payable. Okay, and we have to say that this is payable. I can also have a similar refund function for the seller. Now, some of you already know that this is vulnerable, but I want to write it in this way so that I can talk about the vulnerability later. So again, this is very similar to the previous case. If I'm the seller, I can just call this function and I can say if the balance of the current contract is equal to item value, then that means only the seller has paid his deposit. And so I will just transfer the value to the seller. Okay. So we have functions for putting down deposits. We have functions for getting refunds if the other party does not put down a deposit. We have a function to declare whether we think the item was delivered or not. And now, of course, at the end of all of this, we should have a function that decides how to send the value, how to divide the money between the two parties. So I can call this one, let's call it divide or divide balance, because it divides the balance of the contract between the two parties. Okay. And of course, when I'm doing divide balance, I would require several things. So the first thing I want to require is that I want to be sure that both parties have declared, right? So I want to say buyer has declared and seller has declared. So buyer has declared, and actually let me write it as another requirement, and seller has declared. Now, if both sides have declared, now I can do several things. I can just say if both of them agree that the item was fulfilled. So if buyer's declaration is true and seller's declaration is also true. So what am I going to do? I'm going to give the buyer part of her deposit back. So I'm going to give item value to the buyer, and I'm going to give twice the item value to the seller. Otherwise, if buyer's declaration is false and seller's declaration is also false, so both of them are saying that the item was not fulfilled, so I have to just refund everyone. So I have to send twice the item value to the buyer, and I have to say send item value to the seller. Okay, And well, the other case is that they don't agree and I don't write anything there, which basically means that they will not be able to get their money back if they don't agree. Okay. So this is my contract now. And let's do an exercise similar to what you have to do for your homework. Let's figure out what kind of vulnerabilities we have here. So one vulnerability that we definitely have is okay. So there is a question in the chat that asks, why do we have two declaration variables for each of the buyer and seller? So one of these just, so this one just keeps track of whether a declaration has been made or not, right? And the second one is the actual declaration. And this is because I want to distinguish between the case where the buyer has not declared anything yet and the case where the buyer has declared that she has not received the item, right? So basically, the point for using two Booleans for each person is that we have three possible cases for each person. The first case is that they have not declared. The second case is that they have declared false. So from their point of view, the item is not delivered. And the final case is that they have declared true. So from their point of view, the item has been delivered. So that's why we have two Booleans here. So this one just checks that a declaration has been made, and this one is the actual declaration. Okay, so let's see what kind of problems we can have here. And again, you have to constantly think from a game theoretic perspective, and you have to also think that if your contract has any kind of vulnerability that someone can exploit, they will exploit it. So we are going to be very pessimistic whenever we are analyzing smart contracts. Okay, so here's the first thing. Suppose that I'm the buyer, and suppose that I pay the deposit, but I don't declare. Or this is an attack that both sides can do. So either the buyer or the seller can perform this attack. So as one of the parties, I take part in this contract. I put down my deposit first. But after I put down my deposits, I'm sorry. And after the deadline passes, I just don't declare anything. Now, if I don't declare anything, then the white balance cannot be called, right? Because this one requires that both parties have declared something. So this is a problem because it basically means that I can freeze all the assets, and then I can maybe ask the other party to pay me a ransom in order for me to make my declaration, because otherwise they're going to lose their money. Okay, so we definitely want to avoid this, and the way that we can avoid this is that we can have another deadline for declarations. So we can have a declaration deadline. And this should, of course, be after the original deadline. So let's say this is 1, 2, or 1, 3, 4, 5. This is again another block number. But the idea is that we have to make our declarations before we reach this block number. Okay. So here, when I'm doing the declaration, I, of course, say that the block number should be greater than the deadline, and this was the deadline for delivering the item in the real world. But I also want the block number to be less than or equal to the declaration deadline. Okay? And then I can have another function here, which basically says that if some party does not declare, then the other party can get all the money. Okay? So I don't know what to call it. Let's call it report lack of declaration. And this is also public. So the way this works is that I first require that the time for declaration has already passed. So I want my block number to be larger than the declaration deadline. And then I just check. So if the deadline has passed and the buyer has not declared anything, I will pay everything to the seller. If the seller has not declared anything, I'll pay everything to the buyer. If none of them have declared anything, I don't pay anything to anyone. Okay, so if buyer has declared and seller has not declared, then pay everything to the buyer. Otherwise, if the seller has declared and the buyer has not declared, then pay everything to the seller. Okay, so how do I pay everything to the buyer? I just say buyer.transfer, and remember that the total value was just 3 times item value. And here I would just say seller.transfer, and the total value was 3 times item value. Okay, so this solves the problem that if one of the two parties decides not to declare, then after the deadline for declaration passes, the other party can just call this function and they will get all of the money. So now again, if we look at the incentives here, after this point, it's in everyone's best interest to declare, right? Because if you're the buyer or the seller and you don't declare and you let the deadline pass, then you can be sure that the other person will call this function and get all of the money. So with this simple kind of contract, we can now be sure that both sides are incentivized to definitely declare. Okay, so this is the first problem that we had to solve. But the other problem we have here is that people can change their declaration, right? So they can call this function several times. And that's not something that we really like to have. So let's also limit them in that way. Let's say that you can declare exactly once. Okay, so here I keep the things that I had before, but if this is a declaration by the buyer, I also okay, if this is a declaration by the buyer, let's say I require that the buyer has not declared before. Okay, and if this is a declaration by the seller, I require that the seller has not declared before, so that we make sure each person does exactly one declaration. So as you see, I'm enforcing this idea of exactly one declaration as a combination of two different ways. So one way I'm enforcing this is that I have these requires here, which make sure that no one can declare more than once. But I'm also having a game theoretic thing here, which says that if you don't declare, then the other person can basically steal your money. So everyone's motivated and incentivized to declare. And putting these two things together, we can now be sure that everyone will declare exactly once. Okay. So there is a really nice question in the chat, and this is something that I will talk about later. So, but let me just answer this super fast. It's not the vulnerability that I have in mind, but I will show you how this can make the contract vulnerable later on. So the question is, what if the buyer or the seller directly transfers an arbitrary amount of money to the smart contract? without using this buyer deposit or seller deposit. Wouldn't that break this assumption that we have here? For example, when we're checking the balance, that the balance is 3 times item value? Yes, it would break this assumption. But remember that we talked about 2 specific functions that we can have. We talked about a receive function and a fallback function. And those are functions that will be called if someone just randomly sends money to this contract. Now, the problem does not happen here because I don't have a receive and I don't have a fallback. So if someone tries to just send money to this contract, it will fail. The only way they can send money to this contract is by calling one of the payable functions. And I have only 2 payable functions, buyer deposit and seller deposits. So one cannot just simply send money to this contract. Later on, we will see that there is actually a specific case where they can still send money to this contract, but for now, I'm not going to talk about it. Okay. So now we have almost everything here. But there is still a bigger problem. And the problem that we have is what happens if one side just decides to lie about what's happening in the real world. So this was something that I think I mentioned when I was talking about Bitcoin contracts, but I didn't go into much detail there. So suppose that I'm the seller, and suppose that I'm malicious and I want to somehow extort the buyer. So what I can do is this. I can say, let's first put down our deposits. We both put down our deposits. So now because we have both put down deposits, no one can get a refund. And then after the declaration deadline passes, after the normal deadline passes, I first of all don't send the item in the real world, but as soon as the deadline for me to send the item passes, I call the function declare, and I declare that I have sent the item. Now, this is a lie. I have not actually sent the item in the real world. But what happens from the point of view of the buyer? Well, the buyer can see everything that's happening on the blockchain. So she can see that as the seller, I have already declared that I've delivered the item. My declaration is true. When I say it's true, I mean it's the Boolean true, not that it's a true declaration. Okay, so what happens from the point of view of the buyer? The buyer has 2 choices. She can either declare that, no, the item was not given to me, so my declaration is false. And if that happens, then buyer's declaration would be false and seller's declaration would be true. So when we call divide balance later on, it will not pay any money to any of us. So basically, as soon as the declarations of the 2 parties are different, it's guaranteed that the money is stuck in this contract forever. So the buyer knows that if she actually tells the truth, if she says that the item was not delivered, then she will not get any money back because the whole money will be burned. But if she plays along with my lie and says, okay, I also declare that the item was actually delivered, then here, as you see, if both parties declare that the item was delivered, the buyer will actually get a refund. And this refund is, of course, half of the deposit that she originally paid, but it's better than nothing. So as you see here, there is this problem that the seller can extort the buyer. Now, how can we solve this problem? Unfortunately, the answer is that we cannot solve this. Like, there is no way that you can solve this completely. But there are some ways to make it a little bit better. So one way you can make this better is if, well, you can just go back to your assumptions. Why do we assume that the buyer just wants to maximize her own payoff? Maybe the buyer is not rational. Maybe when the buyer sees that the seller is making a false declaration here, when she sees that the seller is lying, maybe she decides to punish the seller and tell the truth, say the item was not delivered. So yeah, of course, in that case, she loses the item value, but the seller stands to lose twice the item value. So in a sense, the buyer has leverage if the seller tries to extort her. But at the end of the day, if the buyer is rational, and by rational we mean someone who wants to just maximize their own payoff, then the buyer will be extorted here. And that's not great. So what can we do? Well, one thing we can do to kind of fix this is to make sure that the buyer and the seller cannot see each other's actions, each other's declarations before they make their own declaration. And this is something that we had, for example, in our lottery contract. And you have also probably seen this in the homework when you were writing, what was it you were writing there? You were writing an auction contract. So the idea is to use a commitment scheme. What we can do is that instead of having them just declare their choice directly, we can say, okay, they will first declare the hash of their choice, and then after both parties have declared their hashes, they will both reveal it. Of course, this doesn't work very well when you have only two choices. So if your choices are just true and false, it doesn't make sense to hash them, because even after you hash them, the other party can just brute force it, right? They can just check what is the hash of true and what is the hash of false. So instead, what we will need here is that we will need each party to also choose a nonce and then hash their choice and this nonce, and then send this hash to the contract. And then later on, when they want to reveal, they have to give both their nonce and their choice to the contract to reveal the hash. Now, would that solve the problem? This is something that I want to really go into more detail about, and I'm not sure if this session is enough for this, but anyway, so you see here when we were doing this lottery and we were doing the randomness that we had here, where we had portion hashes that everyone would commit to first and then they would reveal. The important point here was that it was kind of simulating simultaneous action, right? So the idea here was that whenever someone was bidding, whenever they were announcing their hash, the only thing that they could see were the hashes of the other people, but they couldn't see the actual portions of the other people, the actual choices of the other people. So they had no idea of what the other person was doing. And because of that, it was effectively as if they were all acting at the same time, right? So even though in the real world they were not acting at the same time, they didn't have any information about the other person's choice. Now, this will not work in our case. So why wouldn't it work? Why can't I just use a commitment scheme? Well, the commitment scheme, again, gives me a simulation of simultaneous action. But remember, whenever we are using that hash, the idea is that the other person cannot invert the hash and figure out what our choices is. What our choice is. So as Bob or as the seller, what I can do is that I can choose a nonce, and let's say my declaration is true or false. I just put these two together and I hash it. and I declare the hash to the contract. Now, at this point, the buyer, or Alice, cannot figure out what my choice was, right? Because she only sees the hash. But it's in my best interest to make sure that she knows what my choice is, right? Because this whole idea of extorting the buyer was based on the premise that the buyer knows that I have already committed to declaring that the item was delivered. So now, as the seller, what I can do is that I can just say, okay, if this is the case, then I send my hash to the contract. And instead of sending the actual item to the buyer, I just send a message to the buyer. I was supposed to send the actual item, for example, by post. I just send a letter by post. And I say, hey, by the way, this is my nonce. And my choice was to say that the item has been fulfilled. And you can just compute this hash and verify this. So again, the buyer would be extorted because she can see the hash that I have committed to on the blockchain. And she has also received a message from me that gives her the nonce and the declaration. And she can just verify that the declaration was true. So the declaration was that I have given the item. And if she hashes the nonce and this declaration, she gets the right hash. So I can prove to her that I am playing true. I am saying that the item was delivered. And this is all we needed for the buyer to be extorted. So now again, the buyer has to go through the same mental process that I either accept the lie and get back half of my money, or I tell the truth, punish the lying seller, and get none of my money back. And again, if she's rational, she will get half of her money back. So as you see, this is a fundamental problem. And the fundamental problem is that even though we should have simultaneous action, we should have a case where the buyer and the seller declare their choices at the same time. We cannot have this using commitment schemes because now the person who's who's playing the game, the seller, it's in his best interest to show his choice to the other side. So commitment schemes only work if each player's best interest is to make sure that other players don't know their choice. And this was the case, for example, in this lottery contract that we had. And it is also the case in the auction contract that you have to write as part of your homework. But in this escrow contract, because it is in the seller's best interest to reveal the choice, a commitment scheme will not work. Okay. But anyway, this is still a good contract in the sense that, well, we don't have to assume that everyone is rational. It's a fair assumption to say that if you take part in a contract like this and you see that the seller is trying to extort you, it's a natural reaction to say, okay, I don't care. I'm willing to lose some amount of money in order to punish the seller and make them lose even more. So rationality is not completely realistic. Now I want to just go back to the last question that was in the chat and talk about what happens there. So the question was, what happens if I just send money to this contract? Because you see, the contract really depends on checking its own balance, right? So, for example, here, when you want to declare, you require that the total balance of the contract is exactly 3 times the item value. So a malicious attacker can transfer some money to this contract to make it so that the balance is not exactly 3 times the item value. Okay? So let me deploy this contract first. And let me actually try to send some money to this contract and see what happens. So let me have another contract. I'm going to call this one attacker. And let's say that the attacker has a fallback function which is payable. So you can just send money to this attacker, or actually, let me give it a name. So the attacker has a deposit function, which is public and payable. Does nothing, it just gets a deposit. And it also has an attack function. And what it does is that it takes the escrow contract at this particular address. So I would call it escrow, let's call it victim, because it's the victim contract. So and let's say my attack function is also public so that I can easily call it. So I get this victim contract and I just send some money to it. So let's say victim contract that transfer, for example, 1 Ether. Okay. Or actually, I didn't need to do that. I can just take its address. Sorry. I always mix these things up. Okay. And it should be payable. And this should also be converted. Okay, so now I have this attacker contract, and when I call attack, it just pays, well, actually, I don't need to even pay 1 Ether. Let's say it pays a very small amount to the victim contract. And the whole reason we're doing this is to break this part of the contract. So suppose that those parties have given their deposits, and now as an attacker, we want to make sure that they cannot do a declaration. And they can only do a declaration if the balance of the contract is exactly this much. So if I can transfer some money to this contract, even a small bit, that's enough to make sure that they cannot declare. And that breaks this contract, right? Okay. So let me deploy the attacker contract. Actually, let me do it with some other account. Okay, so I have the attacker contract. Now I have to first give the attacker contract some money. So let's say I give it 100 Wei. So I deposit. This was successful. And now I attack. And as you see, this was not successful. And if you read the log here, or if you click on debug and go through it step by step, you will see that the thing that is actually breaking here is the transfer function. So you cannot just transfer some amount of money to this contract, because if you look at our contract, our escrow contract, it doesn't have a fallback function or a receive function. And as we talked about this before, when you transfer money to a contract and you don't specify what function you're calling, the receive function will be called. And if it doesn't have a receive function, the fallback function will be called. Okay, and in this case, there is no fallback function and no receive function, so the transaction was just unsuccessful and we couldn't send the money to that contract. So it seems like this contract is safe, but it's not. And so here's why it's not safe. I can actually show you probably in Solidity by Example website. There is a specific kind of hack that's done using the self-destruct command. Okay, so what is self-destruct? Self-destruct is a command that you can put into your contract, and basically what it does is that it destructs the current contract. It makes it so that no one can call any of the functions of this contract in the future. And of course, when you call self-destruct, this contract becomes unusable forever. Okay, so for example, here I can call self-destruct. Okay, And this would make it so that this contract, the attacker contract, will not function anymore, and no one can call any of its functions. But the problem is that when you call self-destruct in a contract, you have to say where the money goes, right? You have to say, so suppose this contract already holds some amount of money and I'm calling self-destruct. I don't want the default behavior to be that the money is just lost, right? So instead of just calling self-destruct like this, we usually call self-destruct with an address. So we put an address here, and the idea is that we do the self-destruct, and then all the balance of the current contract will be paid to this address. Now, what I can do is that I can put the address of the victim contract here. Okay? Now, this attack actually works. So if I have a contract like this, I can first deposit some money into it, and then I can call this attack function. And what this attack function does is that it does self-destruct. So it destructs the attacker contract, but it pays all the remaining balance of the attack contract to the victim contract. And this was exactly what we wanted, right? We wanted to make sure that the balance of this victim contract is anything other than this value here, 3 times item value, because this is what this require is checking, right? So with this simple attack here, I can make sure that this contract breaks. So as a malicious third party, I can just use that attacker contract to make sure that no one can do any declarations in my original contract. And of course, a very simple fix would be to just say that if the balance is more than or equal to this. So the problem was that I was checking that the balance is exactly this much. If I check that the balance is more than or equal to this much, then this particular problem goes away, right? Because if someone else pays some money to the contract or forces a payment using self-destruct, who cares? I have more money in my contract, but everything works as normal. Right? But I have to also be careful about similar problems here and here. Right? So maybe instead of just checking the balances, I have to have some other Boolean flags that tell me whether the buyer has paid their deposit and whether the seller has paid their deposit. And so in buyer refund, I just check that if the buyer has paid the deposit and the seller has not, I transfer the deposit back to the buyer. But generally, this is also a very common attack. And you can see another example of it at this URL. So Solidity by example gives you another one of this. Okay, great. So this is all for this session. I'm stopping the recording now, but I stay and answer any questions that you might have. So have a great time, and I'll see you in the next session.